let me start by sharing my screen. So, thank you very much for the introduction, Steffi and Brandon. My name is Daniel. I'm the co-founder of Adapt, and I'm the basically designer and one of the creators of the Flower framework. Multiple people working on the framework, so I don't want to claim all the credit, but let me tell you what it is. So I think we have a mainly a data science and machine learning practitioner, machine learning researcher audience today. So I'm probably not going to tell you much new with this slide, but if we look at machine learning today, we see that we have a certain structure of how these machine learning models are usually being trained. We usually have a bunch of edge devices, or we could also call them data sources, that have either sensors or something else that generates data. So if we think about a mobile phone, then we usually have certain apps on these mobile phones, and when the user interacts with these apps, the user generates data. So this data is being generated on the device, but then in order to train a machine learning model on that data, we need to upload the data to the cloud. So we have the data from multiple of these devices. We send all of the data to the cloud, and then in the cloud, we basically collect all of this data in a single bucket and then train a machine learning model on that. And we can see these different data partitions on the different devices here. We see how they end up in the cloud, and we also see how the machine learning model then incorporates knowledge or insights about all of these different data partitions represented by the different colors that we have here. This is the common approach for the majority of machine learning models today, but it has some obvious drawbacks. Usually when we train the machine learning model in the cloud, that also means that we run the machine learning model in the cloud. So every time the phone needs some insights from the machine learning model, some inferences, we need to go over the network. We need to ask the cloud, hey, this is my new data point. What's the prediction for that? And then the cloud returns with that. This, of course, limits availability. It increases latency because we always have to go over the network. And then the data uploading part is difficult in itself. So we do have data privacy issues. We do have regulatory constraints like GDPR. Most of us are fairly familiar with GDPR, but then what many people don't know yet is that all over the world, there are similar regulations to GDPR popping up and in place. There are new ways of building these systems, and basically federated learning is one of them. And what federated learning does is it basically just turns this principle around. Instead of sending all of the data to a cloud and training the model there, we send the machine learning model to the devices and train the model on the devices. So this means we leave all of the data on the device and we train the model on device on the local data partition. Obviously, when we train the model only on the local data partition, this means that this locally trained model only incorporates the knowledge and the insights from the data on this single device. So what we need to do is eventually we want to arrive at a model that knows something about all the data partitions on all devices. So what federated learning does is it starts with a randomly initialized model, like most machine learning approaches, and then it sends this model to a bunch of devices. All of these devices train and refine the model on their local data sets. And then they send the updated model to the cloud. And in the cloud, we combine all of these models into a new global model. And this global model, it incorporates the knowledge about all of these devices. So for the data scientists among us, what we do in the cloud is, in most cases, simply a weighted average. How we weight those individual model updates, that's a research question all in itself, and there are multiple approaches to do that. But basically, we just average the models. This has some obvious benefits. We don't need any basically we don't need any big data infrastructure in the cloud. We just need infrastructure to send and receive these models, which is much simpler than the big data infrastructure to handle all of the data sets. And even better than that, we don't have any data in the cloud. So we don't have any data collection. We don't have any privacy topics because we leave the data on the device, and users keep perfect control over the data. So this is, from a regulatory perspective, very advantageous. But then also other topics like the availability and latency are much better off because we have the model on device. If we have the model on device, we always have it available. And usually the latency is also much better if we just execute the model locally instead of always doing the network round trip. What is often overlooked in these cases is that this enables completely new machine learning research cases and production cases. It's not just that we turn it around and keep data on device, but the fact that we train the model on the device enables you to do the training in cases where you weren't able to do the training before. Let's imagine switching from a phone to a robot with multiple cameras to get a 360 view to navigate around. Cameras nowadays, they produce so much data that it's simply infeasible to upload all of this data to the cloud. So in order to train and make use of that data, we actually have to stay on device and train on device. Federated learning is a bit of an extreme case because it moves all of the training really to the edge and to edge devices. But there are multiple hybrid approaches between federated learning on the one hand and then centralized training in the cloud on the other hand. So there are cases where we have, for example, a little bit data in the cloud, and we use that data to pre-train the model and then only move to the edge to refine the model. This data can be either data from real devices, so real collected data, or in other cases, it could be synthetic data. And what we do then is we pre-train the model on synthesized data, and then we go to devices to adapt the model to real-world data. So this is called federated domain adaptation. Next to federated learning, there's something very similar, very related, and this is called federated analytics. And in this case, our main intent is not to train a model on the local data, but it's more to get analytics insights. And the interesting case about this is it uses a protocol called secure aggregation. And what it does is it encrypts each of the local analytics results in a way so that the server side can only read the result if it aggregates one result with all of the other results. So what we end up gaining from that is that we have global insights into this data without ever collecting a single data point in the cloud. And this is a very powerful model. If we imagine, for example, different organizations wanting to get insights into their data without actually putting all of their data into a single database, we can use something like federated analytics to gain insights into those data partitions. This is all fun and good, and there are multiple things we can do, but of course it's not for free. We need to communicate these models with the edge devices. We need to have logic that is aware of these partitions. We need to communicate the results back. We need to average the results, and then do this thing over and over again. And because we go so much over the network and communicate so much over the network, it comes with typical distributed systems problems. And I just mentioned a few problems here, which are also interesting research topics, by the way. So there's a lot of questions around operations. There's the global distribution of these devices can be a challenge. So usually we don't just have users of a mobile app in a single country, but we have users all over the world. So how do we build a system that can handle these users? We do have the data partition, so the individual batches that we can pull from this data to train the models or not the same badges that we can have on as we do with centralized training. And there are a lot of algorithmic challenges involved in that. This is why we set out to build a framework that helps you build these things and allows you to focus on the application that you want to build. And the researchers among us help you focus on the research question that you want to answer. And it's called Flower, as you might have guessed. So Flower, we call it the friendly federated learning framework. You will see why it's friendly, because it plays very well with lots of other technologies that you might be familiar with. Flower was introduced last year. It's open source since day one, since now a little bit more than a year. We demonstrated the ideas behind Flower in a research paper. So if you're interested in some of the thinking that went into it, I encourage you to read it. It's on arXiv. And we are quite happy actually that a lot of major research institutions adopted Flower. So there's we collaborated very early on with the University of Oxford and UCL. We have the University of Cambridge as a major user. They actually decided to use Flower for teaching. So whenever students learn about federated learning at Cambridge, they get introduced to the topic using Flower. And then there are some first industry users as well. For example, Samsung and Nokia Bell Labs, who prototype new systems in their research departments using Flower. The general idea behind Flower is very simple. It's that you take an existing machine learning project, and probably most of us have these on their devices. There are tons of machine learning projects out there on GitHub. You add a little bit of Flower into the mix, and out comes a federated learning project. So the idea is really to allow you to explore the topic of federated learning with as little overhead as is required. The way Flower does this is with the following architecture. We do have this diagram distinguishes between code that is provided by the framework and code that you have to provide to the framework. So on the very right-hand side, we can see that this is your original machine learning pipeline, and we'll see a code example in a few minutes. But usually your existing machine learning example, it consists of two things. It consists of your data, and it consists of your model and the way your model is trained. So the way you would federate this project is you use the Flower client, you write a few callback methods, and then on the other hand, there's basically the Flower framework that takes care of all of the federation part, of the network communication, of the serialization of the stuff that gets sent over the network, of the deserialization, and then of the handling of this averaging, of the selection of the clients, and all of the things that are involved in federated learning. There's also a way to hook into the Flower server on the server side, actually a very powerful way that allows you to experiment with completely new kinds of algorithms and new ideas in how to better federate in certain types of situations and applications. And even though this architecture looks quite simple or quite intuitive, it's actually quite powerful. We do have this decoupling of the server side and of the client side. So what you can do is you can look at what researchers are coming up with, new kinds of federated learning algorithm. There's the first algorithm in that case was federated averaging, but since then a lot of innovation was happening in that space. And what this architecture allows you to do is you can simply take these implementations of these algorithms and plug them into your server, and then federate using the latest approaches. So you don't have to go ahead and read the research paper and implement all of the logic and the math behind it yourself, but you can just plug that in and then combine this with your use case on the other hand. So the things this framework allows you to do is, and this architecture allows you to do, is it provides very good usability, and we'll see that in a second. The compositionality is great because it allows you to write client-side code, which means it allows you to take advantage of basically all of the machine learning frameworks that are out there. You can use PyTorch, you can use TensorFlow, you can use JAX, which is gaining popularity, but you can also use something completely different, or derive gradients by hand if that's what you want to do. You can also use it on different operating systems, and you can even write clients in different programming languages, because there's different way of integrating with it. There's a Python SDK, but there's also an underlying event protocol. And if you don't want to use Python, you can implement the event protocol, for example, in C++ if you want to do something in the robotic space and if you need very good performance. This approach also allows for very good scalability. Each client basically lives in its own process, and we can start these processes on different kinds of machines. So we tested it with up to 10,000 clients, and it worked perfectly fine. We had rounds where we exchanged as much as 90 gigabytes of data per round, and we included really 100 different AWS instances in these workloads, and everything went really well. So that was really was a really good experience. And then because it offers so much flexibility on both the client side and the server side, it allows you to take a unified perspective on different kinds of fleet workloads, as we call them. That's federated learning, but also federated analytics. And then a few of these hybrid approaches like domain adaptation and fine-tuning, personalization, and other things. Based on the core framework, we are building an ecosystem. So we do have quite a few code examples that show you how to get started with federated learning using TensorFlow, for example, using PyTorch. Soon there's going to be an MXNet example and a PyTorch Lightning example. So maybe this shows you that the flexibility on the client side also allows you to take advantage of new and emerging libraries in the machine learning space. And then, based on these examples and the baselines, we also implement additional capabilities around it to make Flower more suitable for example, large-scale simulations. So overall, what we see is that some of the other frameworks, they focus more on simulation, but I think the advantage that you gain by using Flower is basically that you can start on a local machine. You can write a simple federated learning workload on a single machine, and then gradually expand it and make it more production ready. Expand it. The second step that we usually see is the expansion to a large-scale simulation. So this might include a cluster of machines where you want to simulate a really, really large number of clients, because that's what you're going to deal with in the real world. And then after this simulation is successful and you see that your hyperparameters are fine and your model is going to converge if you run it long enough, then the next step can be really global deployment on real physical devices. So if you look at the example I already mentioned, the large-scale simulations that we've been doing, but we've also been simulating workloads on real physical machines. So we had a cluster of Raspberry Pis, and then a number of NVIDIA Jetsons mixed in, and this is what this model allows you to do, basically. So I was promising to show an example of federated learning in hopefully less than 20 lines of code. So let's get started. The first step, obviously, is to install Flower. And in case you already have it on your machine, I included the -u parameter because we just released a new version of Flower today. And here's the example. So the first step is to import Flower and import the necessary libraries that you use. So this example uses TensorFlow. But if you're a PyTorch user, you would just import PyTorch as you usually do, PyTorch and Torch Vision or whatever. The next step is to build your model, and this is also still basically a TensorFlow hello world. In this case, we use an existing model. We use to build an MobileNet v2, and we compile it with an optimizer, Adam in this case. We tell it what kind of loss function to use, and we tell it what kind of metrics to compile with. So plain TensorFlow. Next, we load the local data set. So in the case of federated learning, we were seeing earlier that we do have the data locally on these devices, and usually each device has their own data set. So there's different data in each partition. The way we're showing this here is a little bit, we're cheating a little bit because it loads the same kind of data for every device. What you would usually do if you were to start and to simulate a federated learning workload, you would, for example, start to load the CFAR10 data set, and then you would say, okay, I want 10 clients. Let's partition this data set into 10 partitions to simulate different data sets for each client. But if you have a real-world system, that's basically none of your concern, because this data partitioning happens automatically, organically, just by the data that you have available in each partition. For example, just by the data of a single user that you have in the local mobile app. Up to this point, there's also not much going on. Basically, we have the model and we have the data set. And then next, this is really the core thing to do. We basically implement something called a Flower client. And this Flower client defines 3 methods. The first method is get parameters, the second one is fit, and the third one is evaluate. And these methods, they basically map to what you're already doing in your machine learning pipelines. Usually in your machine learning pipelines, you have a training function and you have a test function. And this is basically what fit and evaluate map to. And by wrapping this inside this Flower client, we allow Flower to basically call into your machine learning pipelines code. So if you look at, for example, fit in more detail, the first step that we take is we set the weights on the local model. So we've seen earlier, we do have this global model in federated learning, and the global model gets sent to the individual device. So we receive these model parameters, and then we need to update the parameters of the local model with the parameters that we received from the server. The next step is to do the actual training. So in Keras speak, this is called model.fit, and we pass it to the local training data. And then as a last step, we extract these weights again, because we want to send the updated model to the server. So we call model.getWeights. And we also add in some other metadata that the server needs. For example, in this case, we add in the number of training examples that we use to refine the model on the client side, because that's what federated averaging uses to do the weighted averaging across all of the model updates that we got. Evaluate works very similarly. And then the last step is to start the client. And this is a simple call to flower.start client. And the important bit here is we handed our CFAR client that we just implemented. And we also tell it the address of the server. So this is to allow the client to connect to the server. It needs to know where the server lives. That's it for the client side. And the server side is, for a simple case, it's that simple. It's just a single call to start server. In this case, we tell it how many rounds we wanted to train, and that's it. And then we can start the workload. The first thing to do, obviously, is to start the server that we've just seen, these 2 lines. And then once the server is up and running, we start the first client, and then we start the second client. And then these clients connect to the server. Once the server has enough clients connected, it starts to select a few clients. It starts to send them the model. And these clients will then execute the fit method. The models will train. The fit method will return the updated models. The server will aggregate these models and then select the next bunch of clients. And basically, you can start as many clients as you want to at this point. So the general idea that we follow is move the model to the data, don't move the data to the model. So this is what basically protects the privacy. This is what allows you to use the model really locally on the device. And this is what Flower allows you to do quite easily. The one thing that I left out of this talk in order to not make it too complicated is if we look at this start server method, this is that simple. It's actually a little bit too simple, almost a little bit too simple. What you can do here is you can pass in additional parameters, and you can also pass in additional code and implementations, and really make the server side as complex as you want to in order to configure what's actually happening on the server side. So we call this the Federated Learning strategy, and there's Flower comes with a bunch of strategy implementations included. So that's what researchers propose in their in the research papers, these new kinds of federated learning algorithms. And there are standard implementations that you can use out of the box, but you can also customize this to your workload. So we see this quite a lot in research, where you have very specific models, or you have different clients which train different parts of the models and things like that. And that's something that is not easily supported by the strategies that are provided out of the box, but that's something that you would build on your own then. And with that, I am ready to take questions. Please check out flower.dev. That's the homepage of the project. The code lives on GitHub, github.com/adapt/flower. And please leave a star on GitHub. Feel free to join our Flower Slack or reach out to me directly. My email is on the slides.